This is for my students, particularly my calc students, but also my pre-calc students. This is about how to plot polynomials and rational functions. And so I've already talked about rational functions, but for the sake of everything being complete, I want to just talk about that first. So if you have a polynomial, you should really think of it as being broken down in some format where it's written kind of like this, where you have all the factors just written out. And you know what, after everything's factored, you can put a 3 or a -4 or whatever you want out front. But those are the only degrees of freedom you have in a polynomial. I want you to think of it this way as opposed to how many x's? 1, 2, 3, 4. So clearly f is 3x to the 4th plus something x cubed plus something x squared, blah, blah, blah. But this is completely useless for graphing. It's just going to confuse everybody. So for the purpose of graphing, it's good if you can in all possibility, if you can get it in this form. You won't always be able to get it in that form, but if you can, that's best. So you have roots at 0, 1, 3, and finally -3. Okay, remember a root is what x value causes this thing to be 0. Right. So because there's no negative out front, we know that we're going to go infinity and infinity, so we're going to go off into this zone. The other option is we could go down into this zone. So you look and see, is there a leading coefficient that's positive or negative? If so, we start up here, otherwise we start down there. Okay, now we know where our starting point is. If we just wiggle through these roots like that, that gives us our plot. Remember, we plot from the right to the left, opposite of the way we read and write. Let me adjust this polynomial now and put some different size roots on here, some different degree roots. So a double root is going to either turn around from one direction or turn around from the other direction. It looks exactly like x squared. And x cubed is going to look like either like this or like this. So it comes in flat, but it still goes through. It doesn't turn around. So those are the most common ones you'll have to deal with. So this coefficient is still positive up here, so I'm still starting up in this region. But now I'm looking at the multiplicity of the roots. So the multiplicity of the 0 is 1. The multiplicity of the root at 1 is 2. I like to put a ring around it to remind myself that there's 2 roots there. And for example, there's 3 roots here, so I put 2 rings to remind myself. And you know, that's just what I do. It's completely unnecessary, but you have to have some way of reminding yourself where everything is. Now we can go ahead and wiggle through. So this time when we get to the root x equals 1, we actually turn around. Then we dive through, and then we do this kind of thing. And you may say, wait, is this for real? And yeah, sure. Let's ask Wolfram Alpha. We say plot, and now let's look at the picture. What did I say? 3x, x minus 1 squared, 3x, x minus 1 squared, and then I had x minus 3 and x plus 3 cubed, and x minus 3 and x plus 3 cubed. And that should work. Alright, so what did we say? We said we were going to cut through a normal root here, then we were going to turn around, cut through, and cubic. Let's see if that's what we did. We cut through, turned around, cut through, and see, this is what a mathematician or a math teacher is going to look for you to do. It's going to just, the root structure has to be correct, and it is. But if you look at the actual plot, what does the actual plot look like? Well, it's got a very different shape, doesn't it? So you really do have a degree 2 root here, but you see how this guy goes down much further, and then it just humps up a little bit. I certainly don't expect you to predict that in a freehand drawing. In a freehand drawing, what I expect is something like this, where I don't care how big or small these peaks are. I really don't. I just want to see that you get the structure of the roots properly. Okay. I think that's all I need you to know for polynomials. We can move on to rational functions. One more quick thing I did want to say about the rational functions, just the way they look. If it's degree 0, it's just a horizontal line. Degree 1 is a regular line. Degree 2 is a parabola. Degree 3 is a cubic, and if you've been in my class, you know that all cubics have a middle point, and they are rotationally symmetric about that middle point. And that's just useful for plotting them. If it's degree 4, what? It's going to go do something like that, right? And degree 5 is going to be like that. And the roots don't always have to be real, but it doesn't. The shape is what tells you the degree of the polynomial. Now, a polynomial can have a higher degree than what it looks like. It can appear pretty much like a cubic, but really it's degree 5. But it can't go the other way. If I have a shape that looks like degree 3, it can't actually be a line in disguise. Okay? So you can bump up, but you can't bump down visually. Okay. Yep. And the roots, you know, so I could put the axis here. This is the x-axis, y equals 0. And in this case, I have all real roots. But if I just move that axis, or move the function, whichever you prefer, now I only have one real root. But the shape of the function doesn't change. So, you know, and you could have the kinks impossible to line up. You could go like that, and what's the degree of this polynomial? Well, let's see, 1, 2, 3, 4, 5, 6, 7. So that's at least degree 7, and there's no way I can have all real roots because I have to pick whether, you know, there's my axis or there's my axis. I can't cut through everything at once. So, you know, just some basic knowledge about these guys. All right. Now, what about rational functions? A rational function is a polynomial over a polynomial, which is why we have to understand polynomials before we can understand rational functions. Okay, so you have two polynomials, and a rational function gets its behavior from how these two polynomials interact. So wherever polynomial 1, I'm just going to call it P1, is equal to 0, then I'm going to call the rational R. Then R is equal to 0. If P2 equals 0, then R is equal to either plus or minus infinity or both. Okay? So that's where you get your asymptotes. You also have horizontal asymptotes, and those are things we have to be aware of as well. So be aware of the following issues when plotting a rational function. Degree of P1 and P2, all roots of P1 and P2, degree, I'm going to say P1 divided by P2, and I'll talk about that. And you have to be aware of the thing I just said. Right, the horizontal asymptotes. If you keep all these things in mind, you should have a really good plot. And there's so many things that can happen. Sometimes polynomial 2 doesn't even have any zeros, and then you get freaky, you know, humps instead of asymptotes. Yeah, so let's look at some of these options. What could possibly happen? So I want to start by talking about, okay, again, horizontal asymptotes is not always, but usually for student exercises this happens. Okay, so degree of P1 and P2 and all their roots. So the first thing you need to be aware of is what's the overall shape. So this bullet point gives the overall shape of the rational function. And let me explain what I mean by that. If you have f equals x minus 1, x minus 2, all over x plus 1. This is telling you the original function f is equal to 0 at x is equal to 0, 1, and 2. This is telling you we have an asymptote at x equals negative 1. So let's put that on a graph and see what that tells us. Okay, so x is equal to 0, 1, and 2. We have roots, but we have an asymptote at x equals negative 1. Okay, what does that mean? What does that give us? Well, now we kind of have to think about where is this going? Is this what is the overall shape? If we don't know what the overall shape is that it's molding itself to, how can we draw it? And so I want you to think of a rational function as a polynomial that's cut by asymptotes. And in this case, we have f is equal to approximately x cubed over x, which is equal to x squared. So we're looking at the shape x squared. And the signs are such that it's not going to be a minus x squared, it's going to be an x squared. So we're expecting this kind of shape to appear. So that's the long-term behavior of this function. But it's cut by these asymptotes. Okay, so what does that mean? Well, let's see. It means if local to this, the origin is where the roots and asymptotes are. That's where the mess is going to occur. So that means if you zoom way, way out, then you would expect to just see x squared. You would just see this picture. But you don't know exactly what's going on in here. So let's just assume way out here it's going to look like x squared. It's not a, there we go, maybe something like this. But we have to come in and wiggle through these points. And oops, we have an asymptote. And what are we going to do? So one of two things is going to either happen. Either this is going to go down and this is going to go up because it's a single root, or this is going to go up and this is going to go down. So the next thing we have to do is figure out which way those wings go. So if you're in calculus, for my pre-calc students, hang in there because we do limits here, so you can sort of say la 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 until I'm done with this part. Okay, so I want to say limit as x goes to negative 1 from the left. I'm going to use the word left, I don't like the minus sign, but as I'm going negative 1 to the left of this function, what is happening? And it's either going to go positive infinity or negative infinity. And I'm not going to bother testing the other direction because it's going to be the other sign. So let's just see what happens. Negative 1 from the left, for example, if you say minus 1.00001, that's a really good test point. So try minus 1.00001. And then if we subtract 1, it's going to be minus 2.00001. And x minus 2 is minus 3.00001. And then it's going to be over, well, what's going to happen? Negative 1 point a little bit more, and then plus 1 is going to be negative 0.00001. Okay, so the important thing to realize is none of these zeros are going to matter, really, because this is 3 times 2 times 1, but they're all negative, right? So that's going to be like negative 6 over negative, this is the thing we call h in calculus. So it's going to be a big number, and it's going to be positive, so this wing goes up, that must mean this wing goes down. And so I'm just going to clean this up, so my pre-calc students, as far as you're concerned, all you have to do is take a point that's really, really close. So if this is x equals negative 1, try negative 0.9999 or negative 1.00001. And that just tells you which way the wing is going. Let's see what Wolfram Alpha has to say about this function. Okay, so it said the same thing as we did. It said it looks, this picture, see, looks like a parabola, but there's an asymptote that goes up and then comes in from the bottom. So on the whole, it just looks like a parabola. But if you zoom in, you see that there's a root at 0, a root at 1, and a root at 2. And if you can't see that, I'm going to actually just change where I'm looking so that I can get a better plot. So from 0 to 3, for example, plot this and see what happens. See, so I wasn't lying to you. We really have roots at 0, 1, and 2. They're just kind of hard to see. I like Wolfram Alpha because it shows you what the function really looks like. But I don't want you to rely on it because it's going to give you a false sense of what's important. And what's important is where the zeros are, where the asymptotes are, and which direction the asymptotes are going. And as you can see, if I don't, Wolfram Alpha does a good job of guessing what a good range or domain and range is for the plot for you. But it's not perfect. So it guesses twice. It makes an educated guess as to what you might want to be seeing. What I really like, though, is one of the plots it gives you is the large range view of what's going on. So you're going to see that you have actually a parabola here, which if you were graphing it by hand, a lot of students wouldn't get that. Okay, I'm going to pause while I erase and set up for the next question. Okay, so I'm just going back to this page briefly. So we have not dealt with horizontal asymptotes, so the next question we will. And when I say usually, I don't mean usually the way rational functions may just appear randomly, but usually in terms of student exercises. So just to be clear what I mean by usually. Okay. Here is a function I wish to consider, and I'm looking at the degree of the numerator over the degree of the denominator, and it's just x squared over x squared is a horizontal line. And this is the most common type, well, I guess one of the two most common types of rational functions that you'll be asked to plot in a math class, which is something that's based off of a horizontal line. Now, the problem with a horizontal line is you don't know if your horizontal line is y equals 3 or y equals -2 or whatever. And that's actually important for the graph. Whereas if what you're doing is just a regular line, all you need to know is it's sloping up or sloping down, and that's enough to make a reasonable plot. But since we actually have a horizontal line, we need to be pretty sure that we have a good long time limit, because that's very important. Okay. So again, calculus, we'll do it calculus way and then the pre-calc way. Limit as x goes to infinity of this function. Okay, my calc students would probably very thorough students I have. So they would work this all out with algebra. And then you would divide top and bottom by x squared. And then you get rid of that term, and then that's 1. And this is not a situation where it matters whether it's plus or minus infinity. There's no absolute value signs. There's nothing weird going on. It's a regular rational function, so you don't have to do it from plus and minus. Okay? So that's fine. So this means the horizontal asymptote is y equals 1. Okay, I'm going to erase all this so that I have room to draw the function. Alright, so I have this function y equals 1 is the horizontal asymptote. Okay, and that is the general behavior of this function. However, I have another problem, which is I have a double root in the denominator. So I have essentially what I'm going to call a double asymptote at x equals 0. Alright, so, you know, are we getting something like this, or are we getting something like this? I don't know. Let's think about this. Now, let's go back to what we said originally. We said that we know that the function itself grabs its roots from P1. So P1 actually has some roots. So let's just plot them in so we know what we're doing here. And that actually clarifies for us. This eliminates, so we cannot cross the asymptote. So we have to approach it. We can't cross either asymptote. And as another comment, the inverse of a rational function is going to be another rational function. So you shouldn't be thinking of the horizontal and vertical asymptotes as being really that different. You're just, if you turn the thing around, then if you turn around 90 degrees, then you just change which is the horizontal and which is the vertical asymptote. And, that's just the way it goes. Or you flip along the line y equals x, you still have a rational function. It's pretty cool. Oh yeah, so we wanted to see if, yes, we agree with Wolfram alpha, and you see based on the scale, you get a totally different look. And that's right. Okay, I'm going to pause and set up for the next one. Alright, so I'm picking another thing that is typical for a student exercise. And in that case, now I said horizontal asymptotes usually. One way we get horizontal asymptotes is when we have the polynomial 1 and polynomial 2 have the same degree. But another way you get horizontal asymptotes is when polynomial 1 has a smaller degree than polynomial 2, in which case you're just going to end up with a y equals 0 asymptote, and so you really don't have to calculate it. But, we can go through the motions and calculate it if you wish. Here's an example. You have a line over a cubic. But the point is that if the inverse function would look like a parabola. But what's 1 over a parabola? Well, when you have more roots in the denominator, you're going to be bringing things down to 0 on average. Okay, so let's go ahead and figure out what this structure looks like. Okay, we have a root at x equals 0. And we have an asymptote at x equals 1. We have a 0, x equals 0. We have an asymptote, and x equals -1. We have an asymptote. But that's going to be kind of messy to draw, so I'm going to just stretch this out a little bit. Okay, so now what do you do? Well, okay, again, look at the structure of the root. I haven't put a negative sign out front yet. If you do, you have to flip everything. But at this point, because we have positive over positive as x goes large, so here's how we would write this. Limit as x goes to infinity of f is going to be just a positive infinity over positive infinity squared. And that's completely illegal, okay? But what I want you to look at is that everything's positive, so whatever's happening is going to be positive, that's for sure. Okay. So we're not allowed to draw those infinities like that. But I do want you to look that essentially you have x over x cubed. So you have about 1 over x squared happening as you go on. So as x goes larger and larger and larger, this is going to go to 0. Okay, so the pre-calc way of doing this, try some value of x that's far away from all the roots and asymptotes. So for example, try x is equal to 100. You can just pull out your calculator if you want, and you can say 99 divided by 101 times 100 to the power of 2. And you see that this is an astronomically small number. That means f is very small. Okay? There you go. Okay, so, but positive. And this means y is equal to 0 is the horizontal asymptote. Okay? But it's positive. So that means we're going out kind of like this. Well, but we do have a 0 in the function, so we have to dive down. Now here's a question. Is this asymptote, the x equals 0 asymptote, is it a single or double or what's going on? It's a double asymptote, so you're actually going to come from the same direction that you left. And so they're going to be matched. matched asymptotes here because it's double. And the other asymptote is just single. But what's going to happen? See, if there were a root down here, which I would like, then I would just make my asymptote I would just make my curve go through the root and up the other side. Unfortunately, I don't have that option. There's no out. There's no way down. I don't have a 0 here. So I actually have to just turn around and go back out. I'm just trapped. I'm just completely trapped. The function has to go somewhere, but it can't go through, so it has to go back up the way it came. Okay, but then this guy is a single asymptote. And so I have to come in from the other side. And again, I'd really like to go through the 0. I have this urge to go through the 0, but I'm not allowed to. It's not permitted. And besides, I have a y equals 0 asymptote, so I'm actually going to connect that way. Let's see if this is the same thing Wolfram Alpha said. Ah, see right here, I was wrong, but it's totally fine. But I missed the fact that there's a max right here. I just dove straight through. So I missed an important part of the structure on this size scale. But if you look at this size scale, it didn't show up. Weird. Okay, so actually I'm going to look at some different scales so I can get a sense of if my big scale is the same as what the plot really is, from x equals minus 10 to 10. I actually haven't done this yet. I'm actually looking with you. So it says it goes up at wherever this is. This is this -1 asymptote. Interesting. It's not giving me y equals, say, -10 to 10. Will it understand what I'm saying? There we go. So it says there's a spike, and then it's coming up this way. It's still not telling me what's happening in this interim. So this is what I'm actually really concerned about at this point, to make sure my plot looks good. Let's go from minus 100 to 100 and see if I can find any evidence of that thing happening. There we go. Okay, it didn't need to be that bad. I could have gone minus 30 to 30. That would have been fine. Minus 30 to 10 even would have been fine. I'm just going to zoom in a little bit for you and see. Yes, so this is what's happening. So this function has a horizontal asymptote y equal 1, but you see it has this loop-de-doo because it wants to go through. It can't. It gets trapped in here. It has to go back out the way it came because there's no root for escape. And then, no root for escape. Okay. And then it flips around and just does what we said it would do. So this is an perfect example of how you need to understand what's going on to capture the essence of this function, but you have to do many, many, many plots before you actually get the same information back out. Okay, so I'm going to just, now that I've seen the plot, I'm going to just say this is the only thing I wish I would have done is something like that. Would have stressed the fact that, and I see why that's happening now, because this asymptote is so powerful that when it hits this root, it still has essentially some kind of velocity. It's a bad way of thinking of it, but it sort of overshoots before it is able to level out, and that makes perfect sense. But it's nothing that you would get in the first pass, and it's not the most important features. So the most important features being the roots and the asymptotes. So hopefully that was helpful, and come see me in office hours if you need some clarification. Just finish with this little list.